Hello, this video is for Stat 360, Handout 12 Part B, and will include pages 12 through 20. Okay, let's go ahead and get started. So this handout is going to use two different data sets. It's going to use the grandfather clock data set that we considered in Part A, but it's also going to use the Minnesota Marriage Amendment data set. So Part B just has some additional considerations of a multiple linear regression model. So the first part here is continuing with the grandfather clock data set. Here's the model that we fit, had age and number of bidders in it. Here is the output from that model. And what we're going to look at here is, on page 2, is understanding the true impact of a predictor variable. So we talked about this a little bit in Part A. So in multiple linear regression, understanding the individual impact of a predictor is not necessarily easy. The reason is often predictor variables influence each other, which mask our ability to measure and understand the true impact of the predictor. So from Part A, we had the correlation matrix that's seen here on the screen. Okay, and we talked about the fact that age and number of bidders were actually correlated with one another. Now the correlation was not real strong, but they were correlated to one another. So the number of bidders here and the age of the grandfather clock are related to one another. So that makes it difficult when we're trying to understand the impact of age or the impact of the number of bidders. One way to investigate this is through the use of added variable plots. So added variable plots, okay, are plots that allow us to understand the true impact of a predictor variable. Now, when I fit a model inside of JUMP, so if I select Analyze, Fit Model here, the price, the age down here, number of bidders down here, kind of our standard process that we've been doing. Over here on the right are the added variable plots. So I've ignored these in all of the discussions that we've had so far, and now we're going to start looking at those. JUMP refers to these as leverage plots, not to be confused with the leverage of an observation. More widely, they're known as the added variable plots. So those plots off to the right will give me information about the true impact of each of the predictors. So on page 14, let's consider how they're actually made. So let us suppose that the effect of the second predictor, let's say x2, is being investigated. So in our example, that would be the effect for the number of bidders. So on the y-axis, what I end up creating with an added variable plot is obtain the residuals from a model that has y given all of the other predictors that you have, excluding the predictor that you're trying to build the added variable plot for. So notice x2 is missing from this list. So again, on the y-axis, I am getting the residuals from this model that does not have x2 in it. So what that is going to represent is the variation in the response that cannot be explained by the other predictors. So a residual, again, takes into consideration all of the predictors that I've used. So the residuals measure the unexplained variation in the response after I've considered these predictors, which is everything except x2. Now on the x-axis, what we are going to do is obtain the residuals from a model where I'm actually using x2 as my response. So x2 is my response there, not y, but x2. conditioned on all the other predictors. I'm going to get the residuals from that model. So what is that going to give me? Well, that's going to give me the unexplained variation in x2 that cannot be explained by the other predictors. So this removes any effect due to the other predictors. So that's what goes on the x-axis. So again, the x-axis contains variation in the predictor that I'm making the leverage plot for, or the added variable plot for. Okay, so that contains the variation in x2 that is independent of the other predictors. So in a sense, that's kind of the new information that x2 is giving me. On the y-axis is the information that cannot be explained in my response by the other predictors. Now, if this plot, the added variable plot, has a form like this here, then that is saying that x2 is going to substantially contribute to my understanding of the response. So we want points that are nice and tight. We want this line to be not flat. It could be increasing or decreasing, it doesn't matter, it just can't be flat. So over here, when the line is flat, or when the trend is flat in this plot, then there's not much to be gained by including x2 in this model. So there's a negligible amount of information that x2 can contribute to the response when that line is basically flat. In our model, recall that each of the p-values for age and number of bidders were significant. So my added variable plots are going to have a pretty substantial trend in them. So here on the left is the added variable plot for age. So you can see that there's considerable trend here. So in other words, age is going to be useful in predicting price for me. These bands here are just the 95% confidence bands for the equation or for the simple linear regression model, that they put in that plot. The p-value reported down here is just the same p-value that we would get here from that test. So they're just bringing that p-value down there to show you the importance of that factor. The number of bidders is also significant. We learned that up above here. We can see that it's a little bit flatter here, so it's not quite as steep as the other. And we also know that the number of bidders is not as useful to the model as the age is. So those are the added variable plots. How about the concept of partial correlations? So here on page 16, we have the idea of partial correlations. So as we discussed previously, for a simple relationship, Pearson's correlation and the R-squared are essentially measuring the same thing. Okay, the R-squared in an added variable plot can be used to understand the effect from the additional information that the predictor is giving me. So here I created an added variable plot. I put a line fit on that. I get an R-squared of 0.77. Now this is in an added variable plot here, or what JMP calls a leverage plot. And what that gives me, again, is an understanding of how much unique information I can get from the number of bidders in understanding my price. R-squared there is 7.77. You can also get that information from a quantity called the partial correlation coefficient. So in JMP, when I'm selecting my correlations and I'm getting my scatterplot matrices, from the drop-down menu here, I can ask for the partial correlations. The partial correlations are correlations that have been adjusted for the other variables. So when I'm looking at the partial correlation between price and number of bidders here, it's 0.8776. That correlation has been adjusted for age because it's a partial correlation here. If you take this correlation right here of 0.8776 and square it, you're going to get the R squared from this added variable plot. So in a sense, the partial correlations are nice because they have been adjusted for the other predictors in the model or that you're considering. Now in practice, rarely are these partial correlations used. I'm not sure why. I mean, I kind of like them. They're being adjusted for the other predictors. But in practice, they're not used very often. The added variable plots, or what JMP calls the leverage plots, are nice because they're just automatically given to me. So I can just glance over and look at them and understand the true impact of each of those predictors. Okay, let's do example 12.2 now. This is going to be on page 17. And for this data, I need to go get the Minnesota Marriage Amendment data. And that's found in our Google folder. In this data set, I have several predictors. Maybe I should start with the response. So the response is just the percent of people that voted, okay, the percent of people that voted yes to Amendment 1. Which Amendment 1 here was that shall Minnesota Constitution be amended to provide that only a union of one man and one woman should be valid. So voting yes here means that they do not want marriage for gays and lesbians. This is saying that it's between one man and one woman. So that's percent yes here. So counties, this is data on counties in Minnesota. So counties that tend to be conservative are more likely to probably vote yes on this amendment. Counties that are more liberal are going to vote no on this amendment. So what are the predictor variables that have been gathered? We got some that are kind of related to just how people voted. This vote was actually during a presidential election, so we have information like what percent of the people in that county voted Democrat, what percent of the people in that county voted Republican. So we got some characteristics that are related to voting, and then I also have characteristics that are just related to the demographics of the counties. So the discussion here on pages 18, 19 are related to the idea of multicollinearity. Multicollinearity occurs in a regression model when two predictors are providing essentially the same information. Multicollinearity should be avoided for a couple of different reasons. Number one, we want a parsimonious model. And what we mean by a parsimonious model is we don't want to overcomplicate the model. I often refer to this as just the keep it simple stupid principle, or the kiss it principle. Don't overcomplicate your model if you don't have to. Additionally, if you include highly collinear predictors, the model fitting algorithm in our software becomes more and more unstable. The reason it becomes more unstable is because it is more difficult to invert the x prime x matrix. You can kind of think of this as trying to get a computer to divide by something that's very, very close to zero. Computers don't like to do that, and that's an unstable thing for a computer to do. When we're trying to identify multicollinearity, we usually identify correlations that are above 0.8, so those would be quite strong positive, or below negative 0.8. Those would be strong negative correlations. So here I went underneath, Analyze, Multivariate Methods, and I put in those first set of predictors, and I'm investigating the correlations for the predictors that are related to voting. Now I'm going to put percent Amendment 1 yes in there first, so that's that top row again. Remember, I want correlations that are high in that top row. I do not want correlations that are high below that top row. So you can see I got all sorts of correlations that are marked here. We have multicollinearity problems with these predictors here. So let's look at number 1 here. So that's the correlation between the number of votes and the number of votes that were for Democrat. Well, certainly those things are going to be related to each other because they're the number of votes. So I don't want to include both the number of votes and the number of votes Democrat in a model. Likewise, I'm not going to want to include the number of votes Republican. So 2 is saying you don't want to include, actually, to be honest, you don't want to include anything with the number of votes here. Not only are they highly correlated, but you can see down here in the first row of my scatterplot matrix that if I do use something that's related to number of votes, I'm going to end up with some high leverage observations. So it really comes down to either using the percent Democrat or percent Republican. Now, p-value or correlation number 3 here says you don't want to use both of those because both of those are correlated to one another. In fact, they're very, very strongly negative correlated. In other words, as the number of votes for one county go up for Democrats, it's going to go down for that same county for Republicans. They're working in opposite directions. So those are going to be negative correlated with each other, and it's going to be quite strong. So what that means from my model building perspective is you don't want to include both Democrat and Republican in the model. So which one do we use? Well, I usually use the one that has a stronger correlation with the response. So here, the Republican has 0.6486. Democrat is actually negative 0.6454. Actually, they're very, very close here. So you could technically use either one of those in your model. I'm going to go with percent Republican because it is slightly, just slightly larger, closer to 1. Now let's look at the multicollinearity issues with the other variables. So here I'm going to use percent yes. I'm going to exclude any of those ones that I've identified up above. So anything with the number or the percent Democrat are not being considered anymore. So I'm going to rebuild my correlation matrix using these predictors. I can see that I have a strong correlation here between the average household size and percent 65 and older. So that's, excuse me, that is exceeding that 0.8 threshold. That's a negative correlation. Okay. So I need to decide which one of those two I'm going to use in my model. I'm going to pick percent 65 and older because it has a correlation with the response of 0.56, whereas average household size only has a correlation of negative 0.22. So I'm going to use percent 65 and older in my model. I also have another one over here that's just under the threshold. This is the relationship between per capita income and percent bachelors. So if I have a lot of highly educated people in the county, then the per capita income is going to go up. And they're quite related to one another. Now technically this doesn't meet the 0.8 threshold, so I'm not going to worry about the multicollinearity between those two, and I'm going to include both of those in my model. One thing I notice under the scatterplot matrix is I'm going to have some issues with leverage when I look at the population per square foot. I believe this is Ramsey County and Hennepin County, which are highly dense counties right in the heart of the Twin Cities. So those two observations right there, two counties, are going to influence my regression model because of the high leverage there. So you're going to want to take that into consideration when deciding what your final model looks like. So what predictors am I going to end up using? I'm going to use, the only one that I'm using out of the voting is percent Republican. And then I got rid of average household size because it was highly correlated with percent 65 and older. So I'm only going to use the predictors here that I have identified that aren't crossed out. Percent Republican, population per square mile, per capita income, percent poverty, 65 and older, and bachelors or higher. And when I fit that model, I get this model output here. I have some predictors here that are not useful. So we can see here that some of these p-values are not less than 0.05, which means that the slopes in these directions, I cannot say that they're different from flat. So the variables that do appear to matter are % Republican, 65 and older, and bachelor. One thing that JUMP does when you start fitting these more complicated models is it provides here a graphic underneath the effect summary. So this is some additional information that you get when you do a multiple linear regression model. This log worth here, okay, if that value is far from 0, that value is large, then that means that predictor is important. JUMP also produces just this little bar graph with this blue kind of line snapped here. Anything that exceeds that line are going to be useful. So again, % Republican, % 65 and older, and % bachelor or higher are going to be the important predictors. And I can identify that here from these p-values as well. So what we're going to do next in Handout 13 is talk about a process that will automatically take out predictors that I don't need. So that's some additional information about trying to build models. Okay, then that does it for Stat 360 Handout 12 Part B, pages 12 through 20. Thank you.